Greetings, Dr. Dan with Optimal Optics here to introduce Unit 8, Refraction of Paraxial Rays Through Thick and Thin Lenses. So we will get through this unit through thick and thin. When I was in practice, I had some patients who thought that lens was the plural and len was the singular. That is not correct. So on the upper left, I have a biconvex lens. A convex lens is thicker in the center, thinner at the edges, and it is biconvex because each surface is convex. I labeled the first surface as vertex A1, the second surface is vertex A2. If you were going to create the first surface with a compass, you would place the point of the compass at C1 to draw that curve, and if you were going to draw the second surface, you would place the point of your compass at C2 on the left side there. I've constructed normals from the center through their respective surfaces. Underneath the biconvex lens, I have two other convex lenses, also thicker in the center, thinner at the edges. The meniscus lens is created by making the second surface flatter than the first surface. Therefore, the first surface's radius of curvature is shorter, smaller, than the second surface's radius of curvature. The plano-convex lens is flat on one side, and it has the convex surface on the other, with its center I labeled at C2. The radius of curvature of the first surface is infinite, being flat. Now, I placed object M arbitrarily there. I've created my ray coming out from M, bent toward the normal, because we're going from a higher index to from a lower index to a higher index in the lens. And then the ray that exits the lens is bent away from the normal and creating an image at M prime. The biconcave lens on the right is thinner in the center, thicker at the edges, as all concave lenses are. And I labeled the vertices A1 and A2 of the first and second surfaces respectively. Their centers are at C1 and C2. That's where you would place your compass point to create those surfaces. Our object at M, let's create our ray that is bent toward the normal. And then exiting the lens, it's bent away from the normal. And this ray does not intersect the optical axis. It diverges. Underneath, we have a minus meniscus and a plano concave lens. Each of them thinner in the center, thicker at the edges. The meniscus lens is created by making the first surface flatter than the second surface. In the plano-concave lens, one surface is flat, one surface is concave. Now, just to be clear, convex and plus mean the same thing, and concave and minus mean the same thing. Now, the incident light ray that's aimed at the optical center of a thick lens and the exiting light ray from that thick lens are parallel. If you aim the incident light ray at the optical center of a thin lens, it is undeviated. Now we'll let O equal the optical center, we'll let D equal the lens thickness, R1 equals the radius of curvature of the first surface, R2 equals the radius of curvature of the second surface, and we'll label the vertex of the first surface A sub 1. Now we can calculate with the following formula how far the optical center is from the vertex, the first vertex of a thick lens. And the formula is A sub 1 O, that distance, equals D R sub 1 over R sub 1 minus R sub 2. Now, if you plugged in real numbers, you could figure out for yourself that if you have a biconvex or biconcave lens, where the absolute values of the radii of curvature of the first and second surfaces are equal, that means R sub 1 equals negative R sub 2, the optical center turns out to be right in between, midway between the first surface and the second surface. And another important thing to know is the optical center is right on the surface of a thin lens. Now, we're going to talk about thin lenses now. On the left is a thin convex lens with arrowheads on each end. On the right is a thin concave lens with inverted arrowheads on each side. Capital F is a primary focal point, and F prime is the secondary focal point. When you send a ray parallel to the optical axis to the lens, its refracted ray goes through F prime, the secondary focal point. When you place an object at the primary focal point F, its ray goes parallel to the optical axis. The same is true with a concave lens, except the rays never reach those points, but the ray appears to be coming from F prime, and the ray appears to be aimed toward F. Now we define lowercase f as the focal length, the distance from F to A. Lowercase f prime is the secondary focal length, the distance from F prime to A. R1 is the radius of curvature of the first surface from A1 to C1, and R2 is the radius of curvature of the second surface from A2 to C2. If we place an object at point M, the object distance U is a distance from A to M. The image distance U prime is the distance from A to M prime. N is the index of refraction of the medium surrounding the lens. Generally, that's air, so N equals 1. And N prime is the index of refraction of the lens material. And remember, distance is measured from left to right or positive, and from right to left or negative. Now, here are the thin lens formulas that you will use to solve word problems. 1 over U prime minus 1 over U equals N prime minus N over N times 1 over R sub 1 minus 1 over R sub 2. It also equals 1 over F, and it also equals minus 1 over F prime. Therefore, the lens, the vertex, is midway between those two focal points, and F equals negative F prime. The magnification formula, which is the image height divided by the object height, it equals U prime over U, also equals F over X, also equals X prime over F prime. X is defined as a distance from F to M. X prime is a distance from F prime to M prime. Now here are the ray tracing rules to determine where your objects and images are by drawing. You start with drawing the lens in the optical axis. You label F and F prime on the optical axis equal and opposite distances from the lens. And F will be on the left if it's a convex lens, and it will be on the right if it's a concave lens. Then you draw an incident ray to the lens that's parallel to the optical axis and draw the refracted ray through F prime. Then you place your arrow object on the optical axis, extending up to that parallel ray that you just drew, and you find where the ray from the arrow through the optical center of the lens intersects the refracted ray from that parallel ray that you originally drew. And that will be the tip of the image, and then you draw the rest of the arrow image to the optical axis. Now we'll construct objects and images at a plus or convex thin lens. It's important to remember that objects on the left are real, images on the right are real. Objects on the right are virtual, images on the left are virtual. So we've constructed object 1, sent our ray through the optical center, and we find that image 1 prime is real and inverted. Our object number 1 was also real. Now we'll place object 2, real object 2, at the focal point, send the ray through the optical center, which we see as parallel to the ray that we drew previously. Therefore, 2 prime, the image is at infinity. Now we'll draw real object 3 between the focal point and the lens, and we see that produces a virtual image that's erect 3 prime. Real object 4, right at the lens, right against it, produces virtual image 4 prime in the same place. Virtual object 5 produces real image and erect image 5 prime. Now we'll construct objects and images at a minus or concave thin lens. So real object 1 produces virtual image and erect image 1 prime. Real object 2 produces virtual image and erect image 2 prime. Real object 3, right against the lens, produces virtual image 3 prime, also erect, right in the same place. Virtual object 4 produces real erect image 4 prime. Virtual object 5 at the focal point. You can probably guess what's going to happen. The refracted ray through the optical center is parallel to the other ray, therefore 5 prime is at infinity. And we'll do one more. Virtual object 6 produces virtual inverted image 6 prime. So we're going to do a real-life example of creating an image with a biconvex lens, which will be a magnifying glass. This will be our object. It's a lamp with some writing on it and 2 black brackets on the bottom. That will be the landmark that you will use to notice that the image is inverted. So, if you notice, on the image on the screen, there's some writing on the bulb that I can see that's inverted. But you can notice that those black brackets that were on the bottom of the object, they are on the top of the image. Now you may be asking, why, if a convex lens produces an inverted image, do we see images right side up when we look through a magnifying glass, which is a convex lens? If you recall the ray tracing, as long as the object is within the focal length of the lens, and this magnifying glass has a focal length of about 8 inches, you get a virtual erect image. But even if you're outside that focal length, you can still see erect images. And the reason for that is that if the magnifying glass is close to your eyeball or close to the video camera, they combine to form one thick lens, and they produce an erect image. I'll prove that to you by setting up my video camera about 5 feet from some bananas on my counter. And I'll start with the magnifying glass close to the video camera, and you'll see right side up bananas because they combine to form a thick lens, the magnifying glass and the video camera. Then as I slowly move the magnifying glass closer to the bananas, still well outside the focal length, we now have upside down bananas as you would expect. And as I move the magnifying glass back closer to the camera, we once again have erect bananas, which probably explains why you were able to get the condom on them in health class.